thanks for the nice introduction. So I think I want to stay pretty much on the whole topic of pattern that we have, and I'm going to present, and the pattern come along. These patterns are on the mesoscales, and I will be talking about mesoscale cloudiness, basically. This is a talk about these patterns. And I'm going to touch a couple of results with different collaborators. They mainly want to point out Graham Feingold and Fabian Hoffmann because they are here, and Martin Janssens and Pouria Alinahi because they are my students. And you will see the other collaborators in the reference that I'll put. And to set the scene, I want to start with this beautiful image of a satellite image of planet Earth. And there are basically two things I'd like to draw your attention to. So when you look at this image, you can see individual cloud objects, let's say, at a whole range of scales, right? And at the same time, you can also see these patterns where you have basically arrangements of several clouds into such a cloud field, which then gives a pattern. And when we look into some atmospheric science textbooks, somewhere we will find this spatio-temporal range of how clouds matter on all scales in the atmosphere. And on the scale range, you will typically find individual cloud objects. And what's also very interesting is that somewhere in this range of the mesoscale, on the timescales of days to hours, we change view from basically what we see when we look out of the window to kind of the top-down space view, right? Because this is the scales where we kind of change. And this is exactly the scales that I want to focus on. And what's actually missing in this diagram are really these cloud fields, which form this amazing pattern that we have heard so much about already today. And these are these mesoscale patterns in cloud fields. Well, and these mesoscale patterns in the cloud fields are actually a big challenge for our numerical models. And the reason for this is basically that we can kind of reach the scales that we need to model them, but we cannot embed them into the sub-mesoscale and the supra-mesoscale that they interact with. And more specifically, so we have what you would call global storm resolving models that can model the whole globe down to something like 1 or 2 kilometers. So that's great, then you can kind of get the pattern, but you still have the problem that you cannot explicitly resolve what goes on the level of the individual clouds. Then we also have large eddy simulations, which we have seen a lot already today, which go down to 50, 100, 200 meters, but then the scales that they can cover are maybe up to, let's say, 500 kilometers, 1,000 kilometers, so they lack the really large scale input. And so what we of course need to do to properly model is we somehow need to account for what goes on the larger and smaller scales. And we already heard this morning when it comes to global climate models that we kind of use these parameterizations or effective models that we use to capture the scales that we cannot explicitly resolve. When it now comes to the mesoscale and global climate models, then the important thing to notice that global climate models, they have grid box sizes of maybe 50 kilometers or 100 kilometers, and the parameterizations that they use to capture the clouds are basically built on the assumption, they're basically built on kind of on this thinking up to the scale of individual clouds. So basically these global climate models cannot account for all these beautiful cloud patterns that we see. Of course, this would only matter if these patterns also matter for the radiative effects in a climate sense, but they might do because they might change cloud fraction. And so maybe looking back at this shortcoming of global climate models, that they do not see these patterns, it may not come as a surprise that actually clouds in general, but also specifically clouds that evolve on these mesoscales in space and also on mesoscales in time on the scale of cloud processes or cloud responses on the scale of hours to days are actually the largest source of uncertainty for our climate projections. I think this morning Anna already showed a future projection. I have here basically the anthropogenic temperature change since pre-industrial in purple. And this comes about on the one hand due to greenhouse gas warming and is partially compensated by cooling effects from anthropogenic aerosols. And the ranges show the uncertainties that are associated with this two forcing, with the aerosol forcing and the greenhouse gas forcing. And in both cases, you can really trace back that the largest uncertainties comes from scales that we would classify as clouds on the mesoscale. So for the greenhouse gas forcing, it's really the feedback of how mesoscale cloud properties respond to changes in the climatic conditions. And for the aerosol forcing, it's how cloud fields respond on meso timescales, on scales of hours to aerosol particles. Just one more background slide. So why do we heard this already. So we care about the clouds because they interact with variation. And the largest uncertainties are the shallow clouds, which Anna already mentioned this morning, because they reflect solar radiation back to space, and it really matters how much of those clouds we have. And then the second very large uncertainty is actually the extent of envelopes of tropical thunderstorms. And these are important because they trap long-wave radiation. And basically both these features roughly play on mesoscale, on mesoscales that we want to look into. And so the basic idea that I want to talk about, that I want to convey for the rest of the talk, is that I actually think that multiphase processes help us in kind of getting a grasp on this problem of capturing mesoscale clouds. So I think they make our life easier. And the reason that I think that is because they give rise to the self-organization and pattern. The self-organization and this pattern mean an effective reduction of the dimensionality. And I think this can help us to, on the one hand, come up with low-dimensional effective descriptions that, for example, we could then put into the global climate models to close this gap. And this might also provide us a conceptual understanding that we need to really know how we need to construct the closures and the boundary conditions of our models to get a good grasp of these mesoscale cloud fields. And I want to do so for two examples. So first, I will discuss the Stratocumulus clouds that we've heard a lot about today already. So Stratocumulus clouds cover vast stretches of the subtropical oceans, and they give rise to this open and closed cell pattern that we've heard a lot about already. And I said that multiphase processes, specifically moist convection, condensation, rain, can make our life easier because it may reduce dimensionality. So for the Stratocumulus, what does this mean, this reduction of dimensionality? So if we model Stratocumulus clouds, let's say kind of these open cells in one of our detailed cloud simulations, our large eddy simulations, then the complexity is something like 10 to the 9 dimensional or so, right? It's just huge. And as we understand these Stratocumulus clouds somewhat, from our domain knowledge, we can actually bring down all this complexity to just a two-dimensional description, specifically when we are interested only in the radiative effects. And the two variables that we need, if we really want to understand what goes on with these clouds, is on the one hand, the liquid water path. So this is the integrated amount of liquid that we have in the cloud. Just think of it somehow as the thickness of the clouds. And then we have the cloud droplet number, which describes the microstate of the cloud and which is also related to aerosol effects, because the aerosol background, aerosol boundary conditions set how many droplets we have. Good first step already. We have reduced the dimensionality. And now what we want to do is, in this reduced state space that we've already seen, liquid water path, cloud thickness, and droplet number, microstate of the cloud, we now want to derive the dynamics. How does this cloud system evolve? And we do so data-driven, so we take a bunch of large eddy simulations, a large ensemble, and then we come up with these worms, which really are only trajectories in this two-dimensional state space, where each of these lines basically is a large eddy simulation that starts at the magenta point and evolves towards the green point. And when you look at this, you can kind of see that everything moves into the middle. But before we go into this, I have a couple of examples. So in this upper corner here, we start out with clouds which have fairly high liquid water content, so they are fairly thick, and over time they get thinner. That's what you can also see here in the snapshots. Down here, we start with fairly thin clouds that get thicker over time. And in this upper triangle here, we have precipitation, and precipitation breaks up the cloud field and brings us to cloud fractions larger than, which are smaller than 1. And so kind of, this is all the process complexity that we have in our large eddy simulation. Now we want to get effective, simple dynamics out of it. And what we do is we kind of can derive such a flow field in state space, which shows us if we would start with a cloud that has a specific droplet number and a specific liquid water path, we can just follow the flow field to see where it would end up. And most importantly, here's just another view of this flow field where the color scale shows you the magnitude of the velocity of the flow in state space. Then you see that these blue regions are the regions where stuff is not moving, so these are the steady states. And we clearly see that we have the two steady states which correspond to the closed cells and the open cells. And this is what I mean by making our life easier, reducing the dimensionality, right? Because here we clearly see we have these two steady states, and these we've taken all this complexity that we have from the large eddy simulation. In a way, we can boil it down here to the two states that we, of course, also clearly observe in the satellite images. Well, and this flow field shows you that you have these two steady states. Now I made this point that it's multiphase processes which help us get these two states. And so let's look into this. Let's look into which processes are actually shaping the flow field that we see here. And these are mainly evaporation and rain formation. So these are basically phase changes between water and liquid phase that we are concerned about. To understand this a little bit, I've here a sketch of such a cumulus cloud. And the first process that is important is that typically the air at the top of these stratocumulus clouds is very dry, and then the clouds, we have mixing at the top of the cloud, which then kind of eats away the cloud base and makes the cloud thinner, and this kind of explains the motion that we have in state space in this direction. And then processes that make clouds thicker are radiative cooling at the cloud top and surface moistening, basically surface fluxes from the ocean. And this explains roughly the structure that we have in the liquid water path dimension. Of course, for this two-state feature, what's most important is this direction, where we kind of have this drastic motion from basically from the right to the left, from the high droplet numbers to the small droplet numbers. And this is related to precipitation and specifically also washout. So precipitation means you take two small droplets and make a big droplet out of it. So this reduces your droplet number, but then you have a positive feedback that this rain also washes out the aerosol, and aerosol means that you get even bigger droplets and a positive feedback there. And so in this sense, these are processes that are related to multiphase and basic precipitation, rain, which then give rise to the self-organization into the open and closed cells. Yeah, and with this, I would like to now go to the second example that I'm going to discuss. The second example are trade cumulus clouds. So these are fair weather clouds in the trade wind regions over the oceans. And they are very distinct because they come in all kinds of different shapes and patterns, not only in open and closed cells and streets, but they also come with stuff that looks like what we see here. Yeah, I forgot to mention, so these are, I should have said that before, so all the images you see are roughly on scales of, 250 to 1,000 kilometers. This is all the scales of the images you see. And when we now think about these trade cumulus, of course, the first question is, well, how can we describe all these patterns? And what people first did is, well, you take a bunch of cloud scientists, they look at a bunch of satellite scenes, and then they say, oh, well, look, this looks like a sugar. And maybe they should have called these worms, I'm not sure. So they say, and so a lot of people got together, and then somehow they said, well, we can distinguish 4 distinct patterns. We call one flour, one gravel, one fish, and one sugar. And so this was the first very scientific classification of the patterns that we have. Of course, that's pretty subjective, and also people usually don't agree. There's many cloud scenes where just experts cannot agree whether it should be a gravel or flour or whatever. So that's it's an interesting way, but not the most robust way of doing it. Of course, as scientists, we usually like to give numbers to things. So the other way of quantifying organization is through organization metrics. And the simplest metric that you can think of would be cloud fraction, right? Just the amount of scene that is covered by cloud. Other options would be clustering, which somehow measures whether the clouds are randomly distributed or whether they tend to aggregate in certain places. We can take the spectral length, of course. We can look at things like the fractal dimension of the clouds, or we can also look at the degree variance when we kind of try to come up with a cellular network description of these cloud fields. And so what my student Martin Janssens did is he took 21 such organization metrics and then performed a principal component analysis on them to see how many effective dimensions we really need to capture the pattern that we see in the shallow cloud fields. And the result was that with only 2 principal components, we can capture 66% of the variance in this 21 organization metrics. And if you take 4 metrics, you go to 80% of the variance. But roughly speaking, we need 2 dimensions, and these 2 dimensions are shown in this figure. So this would be the first principal component, and this would be the second principal component. Basically, the first component is somehow the cloud scale, and the second component is the void size. So if you want to put it differently, the scale of the cloud-free regions, right? This is a way of capturing how the clouds are clustered. And then interestingly, what we find is that the subjective classifications, the sugar, gravel, flour, fish stuff, roughly lie at the outskirts of the distribution of images we get. So the human eye seems to be good at really identifying extremes, maybe, and also good at identifying repetitive pattern. Yeah, maybe one more comment. So strictly from the mathematical analysis, we get these principal components, which are cloud scale and void size. Very similar description could also be obtained by looking into cloud cover and some clustering or aggregation metric. But in general, it's kind of these two aspects that we need. And for the remainder of the talk, I now want to try to connect these two dimensions to processes. And so what we roughly think and looking into currently is that we think that this cloud sail is basically set by self-enhancing variability in the moisture fields. So scale growth and moisture variance. And this void size is shaped by these cold pools that you've already heard about. So this is rain that evaporates while it falls in the subsaturated area under the cloud. And then leads to, when it hits the ground, leads to a divergence, which then gives rise to these large cloud-free areas that you see. But kind of this is the hypothesis, and we are working on really substantiating that. Let's first look into this moisture variance discussion. So Martin Janssens could show that one can really formally describe a linear instability in mesoscale moisture fluctuations, which works as follows. So here we have a cross-section where these small black outlines are basically individual clouds, and the color scale shows you the total moisture. And then what we can see along these big black outline, this is a mesoscale moist patch where we have more moisture than typically on average in the cloud field. And of course, if we have such a moist patch, then we will get preferentially clouds forming on it, right? Because clouds need moisture to form. And now the thing is that these clouds, of course, are associated with condensation and latent heating. And this latent heating drives mesoscale circulations, which are shown here in the gray streamlines, which then pull in additional moisture into the moist patch. And then this means that the moist patch gets even moister and even more prone to form clouds, which then keeps the process going. And kind of this is an instability that it's only moist convection, so we don't need precipitation or radiation, no nothing. So this is really just a feature of moist convection. And what's something that's really interesting also about it is that this instability is coupled to supramesoscale as well as submesoscale features. And so basically, for this instability to form, it depends on what the environmental structure is, and the clouds themselves kind of set this environmental structure, which we can see from the small clouds and the larger clouds here. And then, of course, when you look, it's really these individual clouds and the motion in the individual clouds that project onto this mesoscale moisture fluctuation. And so obviously, the details of how you represent the individual clouds matters a lot, and also the subgrid scale representation in the LES matters a lot in setting the time scale of this aggregation. And actually, on typical scales of up to 50 meters in the LES, the simulations do not converge on the time scale of this moisture aggregation, which is a little bit of a problem if you want to model mesoscale organization. So this is this moisture fluctuations, which we think set this cloud scale in general, because they say where the clouds are and how big they can get. And for the other process, this cold pools, I brought you a movie, which I hope is going to play, yeah? So on the left-hand side, we see the clouds are the gray stuff, the rain is the light blue stuff, and then the moment the rain falls below the cloud, where it's subsaturated, it starts to evaporate and forms these cold downdrafts, which are shown here in blue and red, and which you can see then clearly kind of lead to these openings. And on the right-hand side, we have the surface flow anomaly, and you can really see that when these cold pools hits the ground, they lead to these kind of mini gust fronts, which then spread out and are also associated to the formation of new clouds. And I think in this figure, it's pretty clear why we think that these processes have something to do with explaining the cloud clearing dimension that we see. So this is more an association for now. We are trying to quantify that, and here's a figure which shows from satellite images an index that measures cloud clustering, which is related to, in precipitating clouds, to the drop radius. And what we see is that as the drop radius gets bigger, which means that it's easier for clouds to precipitate, this clustering goes down. And that may seem unintuitive, but the situation seems to be if you have lots of clouds and they can just happily drizzle along, then you don't get this cold pool. But what you need to do is you need to make it hard for clouds to rain so that they get really big and kind of save up all the moisture to then suddenly and intermittently create these downbursts and cold pools, which lead to the pattern and the organization. Yeah, with this I I think I'm just in time to conclude. So I talked about mesoscale cloudiness, this beautiful mesoscale cloud pattern, and I described that the challenge of these mesoscale clouds is really that we have a hard time modeling them because we cannot embed them in the whole range, the individual sub-mesoscale cloud scale and the large-scale drivers of the mesoscale cloudiness. So we kind of need to disentangle it from the supra the sub and supra mesoscale. And the chance I see is that really multiphase processes reduce the complexity of the problem because it gives rise to self-organization, as for example, the simplification that the whole complexity of the Stratocumulus clouds is somewhat broken down into this bistable situation of open and closed cells. And with this, I thank you for your attention and look forward to the questions.
Yeah, thanks for this very clear talk. We're open for discussion now, questions, discussion. Yes, please. Yeah.
So this is a question that I think is addressed to all the 3 talks of this session. The one thing that I noticed is that wind shear doesn't seem to figure anywhere in your either your models or your analysis. Does it mean it's not important? Or
no, it's very important, especially for these cumulus clouds. I mean, this is the reason why we have strong wind shear, and it's important. It matters. Yeah. And especially if you think about maybe a precipitation, it really helps to have some wind shear because then your precipitation falls somewhat displaced from the main updraft of your cloud, and this can help your your cloud to keep going and not kill itself from the precipitation that basically falls down in the same updraft. It's maybe just one example where it really matters. Yeah.
Other questions? Yes, Graham.
I noticed, Franziska, this disentangle mesoscale from sub and supra mesoscale. Can we actually disentangle? Do we have to live with it and find ways of dealing with the circulation at these range of scales and the interaction at the range of scales?
So I don't think we can. I think disentangle is meant in a conceptual sense. We cannot really disentangle just because it's the intermediate scales. It's always the interaction, but I think we need to get a better understanding of the scales of the lag, how strong the lag of time-scale separation is. I think we need to analyze and understand what exactly the mechanisms and the extent of this this entangling is, so that we have a conceptual understanding that can help us to deal with the entanglement that we cannot get rid of. Yeah. At least not in nature. In our models, of course, we can happily do that.
Another hopefully quick naive question. It looks like it's all described as a 2D flat. So the Earth is flat. So no Rossby waves or anything like this. Or Coriolis accelerations or anything. Is it the scale too small for the matter?
So these are actually the scales where kind of Rossby waves, and it's the scales below where the Rossby waves and Coriolis acceleration will become really important. But it's a little bit intermediate, but it's, and you mentioned this is all 2D. Of course it's not, but the nice thing, just a recent result that we have is that when we look into this cloud clustering, then this seems to be also capturing the vertical structure of the cloud field. So basically, if you have a cloud which is somewhat more clustered, then the clouds also seem to be somewhat deeper. So this may be a little bit more general comment. So I really hope that even in the 2D structure, which is nice because we can so nicely observe it from satellite, somehow is a proxy or has the imprint of all the other processes that are there. That's a little bit of a hope. And at least for the clustering and the horizontal dimension of the cloud, there seems to be an association.
Okay, there's time for one more. Yeah, if you can use the mic.
Hopefully that works. Quick question. I've seen a few talks now that are trying to break down this whole system into the 2 parameters. And the one that confuses me is the n parameter, because in a typical cloud, you must have a distribution of different things, and you also have a difference between whether it's liquid or ice. So is it because you're thinking about a different type of cloud, or you're just looking at means, or what?
It's a mean, so you're absolutely right. There is all that complexity, and we heard about that yesterday. So I think we've only heard about warm clouds so far, so we have left the ice out, right? So we have left away all the complexity of the ice, and we are dealing with droplets which are at least round, so we do not have to care about that. And so we have used it as a rather broad parameter, which I think of it tells you whether the cloud is going to precipitate or not, right? And there, of course, you could blow up the complexity and take into account, and it actually matters a lot for whether the cloud will rain, how broad the distribution is. But for the sake of simplicity, so
if you're looking at a deep convective system, you wouldn't be doing this. It's really, I think, because you're looking at the Stratocumulus, or you're focused on that.
Yeah, the shallow clouds.
Yeah.
It's a good, well, it's a good question. So actually we find that this decomposition in void size and cloud scale also works for deep convective clouds. But of course this is the more pattern-based space, right? This is not this is not the space where we actually have the droplet number. If we wanted to do an analysis in this liquid water path droplet number space for deep convective clouds, I guess we would need more dimensions. I don't know what you would think. We would.
Thank you.
I guess. At least something which tells you how icy it is, something which shows you a glaciation fraction or so.
Okay, Cece, please go ahead.
Maybe just a follow-up question about the N parameter. So have you considered the sensitivity of your cloud field to the shape of the DSD, the droplet size distribution, perhaps within the same N parameter?
So I mean, I guess we could just repeat our simulation with a different shape of the droplet size distribution. I assume this would slightly shift, this region where we get precipitation or not, but I don't think that it would fundamentally change the picture. But I should hand maybe the question to Fabian or Graham. So I think on this, it matters, but of course we are really zooming out, right? And on the conceptual level, maybe that's hidden away in one of our parameters, that complexity, right? So there's always complexity conservation, and we put it into the parameters.
All right, thank you again, Franziska.